Let's have a look at another question. This is a question regarding chapter 9, that is waves HL. A lens from an optical system is coated with a thin film of magnesium fluoride of thickness D. Monochromatic light of wavelength 656 nanometer in air is incident on the lens. The angle of incidence is theta. Two reflected rays, X and Y, are formed. X is a ray that is reflected from the front of the surface. Y is a ray that is first refracted, reflected, and then refracted again from the given diagram. The following refractive indices are available. Air has a refractive index of 1. Magnesium fluoride has a refractive index of 1.38. Lens has a refractive index of 1.56. The lens having a higher refractive index is what helps us understand the reflection that is happening here. Next, predict whether the reflected ray X undergoes a phase change. Yes, since X undergoes the phenomenon of reflection, it undergoes a phase change of pi. Pi radian. This is the amount of phase change. The thickness of magnesium fluoride film is D. For the case of normal incidence, that is theta being equal to 0, state in terms of D the path difference between the reflected rays X and Y. Here, since we take normal incidence into consideration, the path difference between the two rays is such that the ray undergoes an additional distance of D here and another additional distance of D here when compared to ray X. So the total path difference or the total additional distance traveled by Y when compared to X, which is also what path difference is called, is 2 times D. This is a simple way of calculating the path difference between the two rays X and Y. Calculate the smallest value of D that will result in destructive interference between ray X and ray Y. So for destructive interference, we have the relationship 2D n is equal to lambda, or I can rewrite the equation as D is equal to lambda over 2 times n. Here lambda has a value of 656 nanometer. N is the refractive index of the medium involved, that is magnesium fluoride, which has a refractive index of 1.38. When substituted, we get the value of D to be approximately 119 nanometer. Moving on to the next question, or the next part. Light from a point source is incident on the pupil of an eye of an observer. The diameter of the pupil is 2.8 millimeter. Draw on the axis the variation with diffraction angle of intensity of light incident on the retina of the observer. Here we have a single slit diffraction that is occurring, and the diffraction pattern that is formed for a single slit diffraction is as follows. The single slit diffraction pattern has a central maxima followed by secondary minima and maximas of decreasing intensities. This is the diffraction pattern that is, or the intensity pattern that is formed for single slit diffraction. Moving on to the next part. Estimate in radian the smallest angular separation of two distinct point sources of light of wavelength 656 nanometer that can be resolved by the eye of this observer. So here we have the minimum or the smallest angular separation. For this we use Rayleigh criterion, which says that the smallest angular separation theta in radian is equal to 1.22 lambda by b. We substitute the values for lambda given as 656 nanometer and b as 2.8 millimeter, which helps us arrive at the answer for theta at 2.9 into 10 to the power of minus 4 rad or radian. So this concludes the solution to the entire question. Thank you.